Hey guys, today we'll be going over some interesting algorithms that we'll be implementing recursively. So you've already seen a lot of different recursive functions, and one of the main uses for recursive functions that we've been doing so far is iterating through a list. And all of these have the same sort of pattern going on, where there's a base case with the empty list and a recursive step that usually pattern matches on the head and the tail of the list. So that's the first element, just this X, and the rest of the list. And then what we do is we do something and then combine it by calling the function again on the rest of the list here. All right, let's actually take a look at some examples of functions that use this pattern of iterate through a list, one element at a time, recurse, and do something at the empty list, return some value. So product is a function that's going to take a list and multiply every element inside that list together. So the way it's going to work is we're going to iterate one time in the list. So we're going to have this pattern. I'll put it here to fill in. Okay, we need to fill in these dots here. So what we're going to do is we're going to pull out each element of the list and we're going to multiply it against the product of the rest of the list. And at the base case, so if we start at the recursive step and we run through the evaluation of it, we're going to have product of, let's say, the list 1, 2. And remember, the list 1, 2 is the same. That's just a special way of writing 1, 2, empty list. So this is going to pattern match to this case here, okay, where X is 1 and X's is 2, empty list here. And this will evaluate, so running one step of evaluation here, it's going to become 1 times product 2, empty list. And of course, now we do the same thing for the next product, and we end up with 2 times product empty list. Now you'll see what we already wanted to accomplish is like already done here. Okay, so we're already kind of finished our work by the time we get to the empty list. So what we need now is something to multiply against that isn't going to change what we've already done. And of course, everybody should be able to figure out if you multiply something by 1, okay, that should leave everything the same. So then this becomes 1 times 2 times 1. Of course, it becomes 2. Okay, you may have noticed right now, if you try and load into GHCI, that product here, it's giving us an error because product already exists inside the prelude. So we can't define product twice. We could just change the name of it, which I'm sure you guys have been doing when running through some of the exercises I've given. But here's a handy little trick. We could import the prelude explicitly. So usually this is kind of like just already done here by default. But then we could use, this is a nice little thing that Haskell lets you do. We say hiding, and we could hide the product from the prelude. And this way, it no longer gives us an error because we're no longer importing the product that comes from the prelude. Pretty cool, eh? Let's do another example. So reverse is going to be a function that's going to take a list and return another list. It's going to be that same list, but every element is reversed. So reverse empty list is going to equal something, and reverse X, X's is going to equal something. And then we're going to recurse. Now, one trick to reverse here is not going to follow this formula that I laid out completely strictly. What we're going to do is we're going to build a list with plus plus. Okay, so what we're going to do is we need to take X and build another list. Take the head of the list and build another list. So we're going to have X here, and then we're going to put it together with the rest of the list using plus plus here. So we're going to put X into a list by just surrounding it with brackets. So now it's the single list of X. We're going to add it, okay, put it together with the reverse of the other list. But here's the trick here. If X is the first thing on the list, then it needs to be put at the back of the new list, right? So we need to do this in the reverse order. So instead, we'll do the reverses of X's plus plus X here. And we're going to keep doing this, okay? So we can run through the little evaluation here. We have reverse of, let's say, 1, 2 empty lists again. So this is going to pattern match to this case, where 1 is X here. And we're going to end up with reverse 2 empty lists plus plus 1. Which is going to become what? Well, that's going to become the reverse of empty lists plus plus list of 2 plus plus 1. And then what do we want to return at empty list? So once again, it's the same thing as before. When we add the lists of 1 and 2 together, when we put these lists together to make one list, we're already done. And once again, we just need to finish this off with something that's not going to change the work we've already done. So for the empty list and plus plus here, we're going to use the empty list. Once again, reverse already exists, so we'll hide it. Okay, so this way, using the empty list, this will become the empty list plus plus 2 plus plus 1, which will all go together to be the list of 2, 1, which is the reverse of list of 1, 2. All right, let's try a bit of a more interesting example. So zip isn't going to take just one list. It's going to take 2 lists. And what it's going to do is it's going to create a new list with each corresponding element, okay, in the 2 input lists put together, kind of paired up in a tuple. So it's going to move through the list and it's going to pair up corresponding elements of the list into a tuple. So as an example here, zip of 1, 2, A, B should return the tuple of 1, A, 2, B. Okay? Now, you do have to cover this scenario. Okay, what if one list is bigger than the other list? So what if you have almost the same thing? But this list is bigger. It should still return the same thing. It should just stop at wherever the shorter list is. It'll stop pairing things together. Okay, so how would we write zip? So let's start with the recursive case here. We would have both. We would have x colon x's and y colon y's. So this is assuming that there's at least one thing in each list. So if we do have one thing in each list, so we're gonna have to do something and then recurse on the rest of both lists, right? So if there is one thing in each list, we'll pair it together in a tuple, okay? And then we'll put it back into a list. Either we can do colon or we can put it into a list and use plus plus. It doesn't matter, it's the same thing. Whoops. Now we need to cover the case, okay, what if these lists are empty? So you might be tempted to at first write pattern match to both empty lists. But then you remember, okay, what if one is empty and the other one isn't? This case here, right? So really what we need to pattern match to is, okay, let's pattern match if this one is the empty list and then we don't care what this one is. Or if this one is the empty, or if we don't care what this one is, the first one is, and this one is the empty list. And in both of these cases, we can return the empty list. Okay, so both of these cases will finish off. Once again, we'll add zip this. So if we were to run through an example of this, how would this example work here, right? Zip 1, 2, empty list, A colon B colon empty list. Okay, if we were to run through this, take 1A. Let's go with the example we have right now. Put it into a list, we plus it with zip colon empty list. Okay. Now this is going to expand, of course, to lists. And then both will be the empty list. Whoops, I think that should have been. Okay, and then once we got to this case, and it would have been the same if this list or this list was bigger than one or the other. Once we get to this case where either of them is the empty list, then we're just adding the empty list back, right? And we end up with A, 2, B. Okay, let's try an even trickier example than this. So the drop function takes an int and a list, and what it does is it removes the first n elements, okay, whatever this int is, it removes the first n elements from the list. So we have two scenarios here. Drop n empty list, drop n axis. So how are we going to do this? So first of all, we should check how many things we have to remove from the list. So if we're at 0, like let's say if we only need to remove 0 things from the list, well, we actually don't have to do anything to the list, right? So if n is greater than 0, what we'll do, then we'll have the recursive case. So that's going to be drop n minus 1 from x's. So what we're going to do is we're going to move through this list, and as long as n is bigger than 0, then we're just going to drop n minus 1 from the rest of the list. But if n is 0, or negative, which we'll just assume to mean also the same thing as 0, then we'll just return the list as is. So like what would drop 0 from x's be? It would just be the same list, x's. However, if we get to the empty list, what are we going to do? Like if somebody says drop 5 things from the empty list, what would you do? You would just return the empty list because you can't drop any more things from it. Okay, so if we were to run through a little example, so we drop 1 from 1, 2. So this is going to become, it's just going to check, is this bigger than 0? Yes, it is. So it'll just become drop 1 minus 1, which is of course 0. And it's going to call this on just x's here. So it's going to be 2 empty lists. And then when it gets called again, now that this is 0, okay, it's going to return x's. So it's just going to return the list of 2, which is exactly what we want here. Okay, we want to take 1 off of the list of 1, 2. Nope, we actually could have used guards instead of the if expression here, but the if expression worked well. But another example, a function that is going to have to do something on a conditional and then recurse is the filter function. So the filter function, it's actually going to take another function as its first argument. And that function is going to take an A and return a bool. And then it's going to take a list of A. And it's going to return a list of A. So basically, it's going to filter a list based on whether or not it's able to satisfy this function. So if the element inside this list returns true for this function, it'll keep it in the list. But if it returns false, it'll get rid of it. So we call the function, let's call it P. And the list, we're going to pattern match over. And we can let's start at the base case here, just because it's so straightforward to go about. How are we going to filter an empty list? Again, it's just like drop. We're not. We're just going to return the list. Now, the recursive case, what we're going to do is going to depend entirely on what the result of P of X is. So let's use a guard here and just put P of X. And that's all we need to put, because this is going to return true or false, and we're testing for true or false. And so either P of X is going to happen or otherwise. So if this is true, what we're going to do is we're going to rebuild the list. So we're going to say X, colon, and then we're going to filter the rest of the list. Filter P of X's. But if this isn't true, well then, what are we going to do here? We're still going to have to call filter. But this time, we don't need to include this X here. So we're just going to do the same thing, filter P of X's, but not add X to the list here. Okay, and just like all of these functions, we almost might as well just get rid of the whole prelude at the rate we're going. Okay, so filter, if we run through an example of this, what would be a good example? Filter, and we would filter a list to see if they are even. Say we have a function that works with evens. It tells you if a int is even or not. So we're going to say filter even the list of 1, 2, 3. Okay, so this is going to become, it's going to start with 1, and what's it going to do? It's going to fail P of X. So P of X is going to be even, okay, 1, and 1 isn't even. So it's going to just call filter again, but this time the 1 is going to be on. And then what's going to happen? Well, now it's going to call even on 2, and this time it is going to keep it. It's going to say 2, colon, filter, even, 3, colon, empty list. Now this gets called, and guess what? Even of 3 doesn't keep it. Goes to this scenario. So, we'll just try it. And then we're at the empty list, and what we're going to return? Just the empty list. It's going to be 2 empty lists, which is the same thing as just list of 2. Okay, and that's filter. Okay, let's take a look at what's possibly the most popular intro algorithm ever, the bubble sort. So the bubble sort is a sorting algorithm. What it does is it takes like a list and it makes sure, it goes through the list and makes sure all the elements in the list are sorted, that they all come in order. So the way it does this is it's going to iterate through the list, and just like inside this GIF here, it's going to check adjacent elements. So it's going to check that for every element, is the element in front of it smaller than it? Okay, if the element in front of it is smaller than it, then they'll swap. Okay, and it'll move through the list doing this, And you'll notice by the time if you start at the first element like this and you just keep moving through each element, moving all the way through the list, by the time you get to the end of the list, it's still not sorted. However, if you repeat this over and over and over again, eventually it will be sorted. And in fact, it will only take at most the length of the list repetitions of this. So you'll have to move through the entire list and then move through it again, the length of the list times at the most to arrive at a sorted list. Okay, let's start off with creating a function bubble. And what bubble is going to do is it's going to move through a list, let's say x-axis here, and it's going to compare x to the thing in front of it in the list. Now the problem here is, okay, we have the first thing in the list, and we have the rest of the list. But we also need the second thing in the list. We want to say if x is bigger than the thing that's in front of it, right? So let's switch up this pattern match a little bit, and let's make this x0, x1, x's. So this is the first thing in the list, the second thing in the list, and then x's. So you'll notice this pattern match is only going to work if there's at least two things here, but we'll get back to that. So we'll say if x0 is bigger than x1, then what are we going to do? We're going to put x1 in front and then rebuild the list, continuing with x0 x's. So now we're going to call bubble, we're going to rebuild the list with x0 now moved in front of x1 here. So we moved x1 to the back here. And otherwise, we're just going to leave things as they are. We'll leave x0 there, and we'll continue moving through the rest of the list. So if x0 is not bigger than the thing in front of it, then we just call bubble on the rest of the list and we leave x0 alone where it is. So we're going to do this as long as there's two elements of the list. This is what we pattern match to, as long as there's two elements of the list. So now we need to take care of the scenario. What if there's more? What if there's one? So we could try out two scenarios here. What if there's one thing in the list? And what if there's nothing in the list? So if there's nothing in the list, this is an easy one. We'll just return the empty list. How do we sort the empty list? The empty list sorted is just the empty list. If there's one thing in the list, oh, guess what? We're also just gonna leave it alone. Okay, how do we sort a list with one thing inside it? We just leave it alone. It's just a list of one thing. And so actually we can shorten this up here. Instead of pattern matching to these two cases specifically, we could just make sure it's underneath this pattern and then be like anything else, any other pattern, X is here, we'll just leave it as it is. Okay, now this is part of bubble sort, and you'll notice it'll work on any list of A as long as it's part of the orderable class, which basically is just saying as long as you're able to do this comparison, say one thing is greater than the other. Okay, but you'll notice this isn't enough. This function alone isn't enough to actually sort something. To actually sort this, what we need to do is we need to call this function until the list is sorted. So we could write a function bubble sort. It's going to take an x's, okay, it's going to take some list, x's, and what it's going to do is say let x's prime equal bubble x's. We'll create another variable x's that calls this function on it. So we'll call the function and we'll get some results, and we'll say if x's prime is equal to x's, then, so in this scenario, calling bubble on the list isn't going to do anything more. It's just staying the exact same thing. That means we must be done. It must be sorted. So in this case, we'll just return x's or x's prime. It doesn't matter. They're the same thing. We'll just return it and be like, okay, this is our sorted list. But if it's not the same thing, then we don't know if we're done yet. So if we don't know if we're done yet, then what we'll do is we'll just call bubble sort again. on x's prime now. Okay, make sure to call on x's prime because we need to call on the thing we're updating that's been updated. And now this function altogether is sufficient enough to actually sort your list. And it'll do it in at most the length of list calls of bubble. However, it might do it in less. Just a note on bubble sort now that I've taught you it, never use it, please. It's extremely inefficient. Basically, the only reason people even acknowledge its existence is it's considered the most intuitive sorting algorithm. So if you were to get a group of elementary school students together and somehow trick them to developing a sorting algorithm, what would be the most likely sorting algorithm they would come up with? Probably the bubble sort. However, you never ever want to use it. Another type of sorting algorithm is the insertion sort. So this is an algorithm that's going to do the same thing as the bubble sort. It's going to sort the list, but it's going to do it in a different way. So the way the insertion sort is going to work is it's going to set up a sorted and an unsorted list. And the trick is that at the beginning, the sorted list can just be an empty list. And then what you do is you take an element, like in this GIF here is showing, you take an element and you insert it into the sorted list. And the idea here is because you know the list is already sorted, you just kind of move through the list, and as soon as you find the spot where it's like, oh, I'm bigger than this guy, then you insert it in. Okay? So you just do this, you move through the list and insert every element of the unsorted list into the sorted list. And eventually you just wind up with one big sorted list. Okay, let's try making the insertion sort in Haskell. So to start off, we're going to create a function insert. And what it's going to do is it's going to take a variable x and it's going to insert it into a list y's. And the idea here is we're going to assume y's is sorted and insert x, keeping it sorted. So to do this, let's use guard. What we're going to do is we're going to pattern match on y's. And using guards, it's going to be similar to the bubble sort. We're going to compare x to the current element in the list. And if it's smaller than it, okay, then that means we could put it in front of y's and it'll still be sorted because y's is already sorted. On the other hand, though, if x is bigger, then what we're going to want to do is we're going to want to take y here, and then we're going to not quite do this. What we need to do is, sorry, this needs to be y's. What we need to do is we need to continue inserting x into the rest of y's here now. So we'll need to insert x into y's. So this way, we'll continue moving through y's until we find the y that it's smaller than, okay? And then insert it there. And if it doesn't find the y that's smaller than, then we'll end up at this case. So we'll end up at the other case of insert x empty list. And what are we going to do here? Well, we're just going to insert x into the empty list here. We're just going to make the singleton list of x. Okay, and now that we got this list, what we need to do is we need to write a function now, insertion sort. And the way insert sort is going to work is it's going to iterate through a list, x-axis. Okay. And what it's going to do is it's going to insert x into the sorted list x's here. So what's happening here? So what we're doing is we're taking the list, the head of the list x here, okay, and we're inserting it into an already sorted list. We know it's an already sorted list because we're calling insert sort on it, right? And we're going to keep doing this until we get to the empty list here. And then once we get to the empty list, we can just return the empty list, because guess what? The empty list is already sorted. So what we're going to do here is, let's say we have insert sort on the list of 4 to 5. Okay, what is this going to evaluate to? It's going to evaluate into insert 4 into insert 4 to 5. I'm actually going to skip a step here. You can imagine eventually it just turns into insert 2, insert 5 into empty list. Okay? So after all of these recursion, all of the insert sort recursions have happened, you wind up with something like this. And then we go all the way back up, inserting one of these things at a time into the empty lists until you wind up with the sorted list. So 2, 4, 5. Okay, because it inserts, go through this one step at a time. So insert 5 empty list here turns into just a list of 5, which then turns into 2, 5, which then turns into 2, 4, 5. Okay, let's talk about one more sort, the quick sort. So the quick sort is a bit harder to visualize, but it's not that unintuitive. So the way it works basically is that you choose a pivot point in the list. So this pivot point could just be any element in the list. It could just be the first element you pull out of the list. It doesn't matter. And what you do then is you partition 2 other lists. So you create 2 other lists from the remaining list of all of the elements that are smaller than the pivot point and all of the elements that are greater than the pivot point. And then you repeat this operation on both the lesser and greater lists that you end up with, and eventually just kind of put it all together into one big sorted list. So how are we going to implement this in Haskell? So we'll create a function, qsort, and we'll just start off with the base case of the empty list equals empty list, and we'll pattern match. And what we'll do is the pivot point will just be the first point of the list. So we'll pattern match on the list, and the pivot point will just be the head of the list, the first thing in the list. And what we're going to do is we're going to have to divide this up into lesser and greater. Okay. And once we have, so we'll just leave this alone for a sec. We'll define these in a second. Once we have the lesser and greater list, what we're going to do is we're going to perform the quick sort on the lesser list and the greater list and put it all together with P in between. Okay, so this way we'll sort one partition of the list, the other partition of the list, and P will be in between. Now, there's a few ways we can go about implementing how to partition things into the lesser and greater list. One way that actually isn't that efficient, you probably shouldn't do it, but just kind of looks really nice, and so it's a good place to start out when learning about this algorithm, is to use list comprehension. So we can say X comes from the list X's, and X is smaller than P. X comes from the list X's, and X is greater or equal to P. We also could have used, let's say, the filter function. We could have said filter X is less than P, X's. Okay, this is another option. And then we would have done basically the same thing, but with greater or equal to. This should actually be less than or equal to, and this should be greater than. That's actually not a big deal. That really doesn't matter, but this is it. This is all that's required to create the quick sort. So you'll notice it actually has a pretty easy definition inside Haskell. So it's a little bit difficult to examine the evaluation of quicksort, but if you the way I like to look at it is I like to break it down into this kind of tree form. So when you were to call quicksort, what ends up happening is it takes the first element here and then it calls quicksort twice again, okay, on either side with everything that's smaller than the first element on this side and everything that's bigger than the first element on this side. And it takes the first element from that, if we go down this side, and breaks it up, does the exact same thing, okay, into two other lists. And by this point, they're at the singleton and empty list, so they just kind of return what they have. So if you go from the bottom and you work your way through this, what ends up happening is you end up having 1 plus plus 2 plus plus empty list plus plus 3 plus plus another empty list plus plus 4 plus plus 5 here. So we'll leave off here, guys. This isn't all of these sorting algorithms. There's too many sorting algorithms to go over in one video. And in fact, I left out one of the, what I would say is one of the most important sorting algorithms to learn, the merge sort. However, this is because it's so important that I want you to focus on trying to learn about it by developing it yourself. So you'll notice if you look at the exercises for these weeks, it's all about doing the merge sort. So I highly, highly recommend spending the time to do those. See you next time, guys.